Today, we are going to unlock a hidden world of software, the code that powers pretty much everything we use, from our cars to our coffee makers. And we're going to explore a truly groundbreaking new tool that's finding security flaws in places no one could even look before. Let's dive right in. You know, every single one of these devices, your car, your smart speaker, yeah, even the very device you're watching this on right now, it all runs on a hidden, fundamental layer of software. But what happens when that foundational code has a secret flaw? You see, all these devices are what experts call embedded systems. They're the critical link between our physical world and the digital one, and they're all controlled by this invisible, low-level software called firmware. The best way to think about firmware is like the central nervous system of a device. It's the most fundamental code there is, and if a bug exists here, the entire device, and frankly, anything it's connected to, is completely at risk. So you can see why securing firmware is so absolutely critical. Okay, so if it's that important, you're probably wondering, why aren't we finding all these bugs already? Well, that question gets right to the heart of the challenge. How in the world do you test software that's so deeply embedded, so tangled up with the hardware itself? Well, the best method we've had so far is a technique called firmware rehosting. What security researchers do is they basically lift the firmware right off the physical device and run it inside a software simulator. This lets them test it at a massive scale, using this automated process called fuzzing, which is just a cool way of saying they throw millions of random bits of data at the code to see if they can make it crash or do something it's not supposed to. But, and this is a big but, there's a huge catch. Rehosting has this massive blind spot, and its name is Direct Memory Access, or DMA for short. And let me tell you, this one function has been a gigantic headache for security testers for years. So what even is DMA? The easiest way to picture it is as a secret, high-speed delivery service for data inside your device. It lets all the different hardware parts talk directly to the memory, completely bypassing the main processor. Now, this is incredibly efficient for speed, but because it operates in the shadows, it's almost completely invisible to those security emulators we talked about. Now, here's where it gets really tricky. This secret delivery service isn't just one thing. Oh no. To squeeze out every last drop of performance, hardware designers has come up with at least 6 different ways to do DMA. Some are simple, some are super complex, and this variety is exactly what makes it so incredibly difficult to build one testing tool that can actually see all of them. And this right here, this is the core of the problem. Up until now, the very best automated tool researchers had, a system called DICE, could only detect the absolute simplest kind of DMA. That means it was completely blind to the other 5 methods. We're talking about enormous, uninspected gaps where security flaws could just be hiding in plain sight. But this is where our story takes a really exciting turn. A brand new approach called GDMA was designed specifically to solve this exact problem, to finally see all 6 types of DMA. So how does it do it? What's the secret sauce? Well, instead of looking for one specific rigid pattern like the old tools, GDMA is dynamic. It actually watches the firmware as it runs, and it learns the unique data transfer patterns of that specific device. It's not about brute force, it's all about intelligent observation and adaptation. The whole process works in 4 key steps. First, it just watches. It looks for memory locations that act like little signposts or pointers. Then it starts gathering clues about what those signposts are pointing to. After watching many runs, it distills all that information down to find the consistent pattern, the true secret delivery route. And finally, it builds a working model of that route, so our security tools can start sending test data right down it. So that all sounds great in theory, but does it actually work in the real world? Well, the proof, as they say, is in the data. And the results are, well, they're pretty staggering. First, the big one. GDMA can successfully model and test all 6 of the common DMA mechanisms. That is a 6-fold increase in capability over any other automated tool out there. Period. I mean, this chart really says it all. The old state-of-the-art method could see one mechanism. GDMA sees all of them. It is literally the difference between peeking through a tiny keyhole and throwing the entire door wide open. And you know what they found when they threw that door open? 6 new, previously unknown, and critical security vulnerabilities in software that people use every single day, all of which, by the way, have now been fixed thanks to this. This isn't theoretical, this is finding and fixing real-world problems. For the folks who do security testing, this is a total game changer. It means they can see so much deeper into the code. In some tests, GDMA increased the amount of code they could actually analyze, what's called code coverage, by over 150%. It's basically lighting up huge sections of the firmware that were completely dark before. But look, this is more than just an academic exercise with some cool numbers. So let's talk about what these technical wins actually mean for the safety and security of the devices that we all rely on. Take this as a perfect real-world example. GDMA found a nasty bug in an operating system used for smart home devices. The flaw was actually pretty simple. After sending a message, the device expected a tiny little confirmation message back. But a hacker could send back a much larger one, overwhelming the device's memory, and that could cause it to crash, or worse, even run malicious code. But here's the truly groundbreaking part. This bug wasn't just anywhere. It was in something called the hardware abstraction layer, or HAL. You can think of the HAL as the absolute bedrock of the software, the part that talks directly to the physical silicon chips. Most security tools can't test this layer. They are literally forced to just trust it. But because GDMA analyzes the entire firmware from the outside in, it doesn't have to trust anything. It can find bugs at the very foundation of a system that other methods would have completely, totally missed. So, the bottom line is this. For years, a huge and absolutely critical part of the software that runs our world has been effectively untestable, a total black box. GDMA is finally lighting up one of cybersecurity's darkest corners, and it's finding flaws we never even knew how to look for. And that really only leaves one question. What else has been hiding in the shadows all this time?